What does it mean for a function to be continuous? Well, the idea is pretty simple. It's that you can draw the function without lifting up your pencil. So there's no holes in the graph, there's no jumps in the graph or vertical asymptotes. But that's not very mathematically precise to just say, oh, it's something you can draw without lifting up your pencil. So there's got to be a little bit more of a mathematically precise way of saying it. And now that we know about limits, we can talk about this in a more precise way. So a function f is said to be continuous at x equals c if these three conditions are satisfied. So first of all, f of c has to be defined. So c has to be in the domain of the function. Second, the limit as x approaches c of f of x has to exist. And third, those two things have to be equal to each other. So actually, if the third condition is satisfied, then it implies that the other two ones are satisfied. Because if these two things are equal, then, well, that means f of c has to be defined, and this limit has to exist. So it's really the third condition here that's kind of important. It implies the other two conditions. Okay, so what does this mean? Well, it means that if you're trying to find the limit as x approaches c of a function f, if it's continuous, you can just plug in c to find the answer. Okay, so let's look at this graphically. Okay, are the following functions continuous at c? Well, notice here, f of c is not defined. Okay, so that first condition is not satisfied. So this is not continuous. It's got a hole in the graph. Okay, let's actually go down to this one down here. Is this one continuous at c? Well, no, it's got a jump in the graph, but the idea here is that the limit as we approach c from the right and the limit as we approach c from the left are not the same. So the limit as x approaches c, that ordinary limit, does not exist. So that second condition is not satisfied. Okay, now if we look at this example right here, notice that f of c is defined, and the limit as x approaches c of f of x exists, right? It's this number up here, but those two things are not the same. Okay, this would need to be filling in that hole right there. They're not the same, so actually the third condition is not satisfied here. So none of those three functions we've looked at are continuous. Now, what about this one? Yeah, this is continuous, right? There's no issues. F of c is defined. It's this value right here. The limit as x approaches c exists. It's also that value. And so this function is continuous. Notice we can draw it without lifting up our pencil. Here we have a jump. Here in these two ones, we have a hole in the graph. So those are not continuous. Okay, what does it mean for a function to be continuous on an interval? Well, function f is said to be continuous on an open interval a to b if f is continuous at every point inside that open interval. So are these functions continuous on the open interval a to b? So here we have this interval from a to b, and the question is f continuous for every point at every point inside this open interval? Well, no, there's a problem point right here. It looks like this is x equals 1, right? Notice the limit as x approaches 1 doesn't exist. As we approach from the right, it's infinity. As we approach from the left, it's this number. By the way, even if both limits were infinity, remember, infinite limits don't exist. Okay, so this is not continuous there. Okay, what about, is this function continuous on the open interval a to b? Well, it looks like we got a problem, but that problem is outside of our interval a to b. So this function actually is continuous on this interval a to b. Okay, well, let's look at a couple theorems. So first of all, if f and g are continuous at some point c, then f plus g will be continuous at c. Or think of it as, suppose f and g are continuous everywhere, well, then f plus g will be continuous everywhere. And same thing with f minus g and f times g. So adding, subtracting, multiplying continuous functions is still going to preserve the continuity. Now, dividing will preserve continuity as long as we're not dividing by 0. So f over g will be continuous at c, provided that g of c is not 0, provided we're not dividing by 0. And it has a discontinuity at c if g of c is 0. Okay, so you can add, subtract, multiply, divide continuous functions, and you get continuous functions as long as you're not dividing by 0. So one of the things that this implies is that polynomials are continuous everywhere. Okay, any polynomials would be nice continuous function, right? There's no jumps, holes, anything like that. And rational functions, so a polynomial divided by a polynomial, will be continuous at every point where the denominator is non-zero. They'll have discontinuities at every point where the denominator is 0, every place you're dividing by 0. Okay, so let's look at an example. For what values of x does this function have a discontinuity? Well, notice it's a rational function. So what we need to do is figure out what values make the denominator be 0. So let's factor the denominator. Turns out it factors to be x minus 3 times x minus 2 The numerator is a difference of squares. The factor is the x plus 3 times x minus 3. So where do we have our discontinuities? Well, we have our discontinuities at x equals 3 and x equals 2. Okay, now it doesn't matter that this x minus 3 factor cancels with this. We still have a discontinuity there. Now at x equals 3, it'll be a removable. It'll be a hole in the graph at x equals 3. At x equals 2, though, we have a vertical asymptote. But the point is, it's still going to be discontinuous at those two values. If you were to graph this, there'd be a hole at x equals 3, and there'd be a vertical asymptote at x equals 2, but we'd still have discontinuities at those 2 points. Okay, find the values of x, if any, at which f is not continuous. Well, the first one is a polynomial, so this is continuous everywhere. So CTS will be my abbreviation for continuous. This is continuous everywhere. What about this one here? We have a rational function. Well, notice the denominator, x squared plus 9, is never 0. In fact, it's always got to be bigger than 9. X squared plus 9 is always, x squared is never negative, right? And we add 9, it's always going to be at least 9. So the denominator is never 0. So this is also continuous everywhere. Okay, there's no place that makes no value of x that makes the denominator 0. I guess if you plugged in an imaginary number like 3i, it would make it 0. But it's continuous for all real values. Okay, what about this? Well, we have a difference of squares this time in the denominator. And so notice the way that this factors is x plus 3 times x minus 3. And so it's going to be discontinuous at x equals negative 3 and x equals 3. And again, their discontinuities are going to be for different reasons. So for x equals 3, that'll have a vertical asymptote. At x equals minus 3, since these cancel, it'll have a hole in the graph. Okay, what about the last one here? We have x over 3x squared plus x. Well, again, we can factor the denominator. We can pull out an x from both of those two terms and write this as 3x plus 1. Okay, at what values is this discontinuous? Well, notice at x equals 0, that will make this 0, so certainly x equals 0. Now, what's the value of x that makes that 0? Okay, it's not just x plus something or x minus something. So I guess we could kind of solve 3x plus 1 equals 0. Subtract 1 from both sides. We're going to get 3x equals negative 1. So x equals, if you divide both sides by 3 here, x equals negative 1/3. Okay, so x equals 0 and x equals negative 1/3. Those are the places where this function is going to have a discontinuity. Okay, now for our final examples, determine whether the functions are continuous at x equals 2. So we're looking specifically at x equals 2. Are these continuous at 2? Well, notice f is not continuous at 2 because we're dividing by 2, right? It's a rational function, polynomial over polynomial, and any value that makes the denominator 0, it will be not continuous there. Okay, what about g? Now you might think, well, g is also a rational function. It's very similar to this. Only g, so first of all, f of 2 was not defined here, right? So it's not continuous, right? If you look at those three conditions, is f of 2 defined? No. Now what about here, g of 2? G of 2 is defined, right? G of 2 is 3. In fact, let's write this down. G of 2 is 3. Okay, so the question is, what about the limit as x approaches 2 of g of x? Okay, does that exist? Well, what's the limit as x approaches 2 of g of x? This will be the limit as x approaches 2 of x squared plus 3x minus 10 over x minus 2. Now, you might think, well, why was it equal to that? I thought g of x is not this. G of x is this whole function here. Why is it this? Well, the limit as x approaches 2 has nothing to do with how the function is defined at 2, only how it's defined when x is near 2. And when x is near 2 but not equal to 2, in particular when it's not equal to 2, the formula is like this. So when we say the limit as x approaches 2 of g of x, we can say limit as x approaches 2 of this formula, because that's what the formula is when x is not 2. Okay, and here we've learned how to calculate these. We've done these before already. So how do we do this? Well, we factor things. And the numerator, it turns out, you kind of have to get good at factoring in this class. It turns out it factors to be x minus 2 times x plus 5. Okay, and so notice these x minus 2 factors will cancel, and we get limit as x approaches 2 of x plus 5, and that answer will just be 7, right? Plug in 2, we get 7. So notice g of 2 is defined, it's 3. The limit as x approaches 2 of g of x exists, and that's 7. But notice, are those the same? They're not the same. So of our three conditions, remember g of 2 had to be defined, it is. the limit as x approaches 2 of g of x has to exist, and it does. Okay, so the first two conditions are satisfied for continuity, but those two things are not the same. So the function's not continuous at 2. Now, what's really going on here? Well, g of x, what does this g of x function look like? Well, g of x looks a lot like x plus 5, right? When we simplify this expression here, this right here, it simplifies to be x plus 5. So if we were to graph the function, it looks a lot like x plus 5. So it has a y-intercept of 5 and a slope of 1. But actually, at 2, if we go over here to 2, there's supposed to be a hole in the graph there at 2, and it's defined to be 3. Okay, so we get this hole right there at 2. Okay, and it's defined to be 3 down there. Now, if this, instead of defining it to be 3 there, g of 2 is 3, if we had defined it to be 7, okay, g of 2 is 7, this point, instead of being down here, would be filling in that hole right there. Okay, and then it would be continuous. In fact, that's exactly what we have in part C. Now, I called it h, but notice it's the same function, only I defined it to be 7 at x equals 2. So here's our function x plus 5, right, which is really just this when x is not 2, right? This thing simplifies to be x plus 5, right? When we factored it, we got this, and we cancel those factors, we get x plus 5. And again, x plus 5 has a y-intercept of 5 and a slope of 1. It looks like this. It would have a hole in the graph right there at x equals 2. But g of 2 would be 3 for this function, whereas I was calling it h here. H of 2 would be 7. It would actually fill in the hole rather than being down here. So this one is continuous. So part C, the answer is yes, it's continuous. Here, the answer is no. Okay, so if you were just going to call this, for example, k, okay, g of x, you could ask what value of k would make g of x continuous? Well, what you need to do is say, well, g of 2 would be this k value right here. We'd put k instead of 3. We compute the limit as x approaches 2 of g of x the same way, and we get 7 as a result. And if we want it to be continuous, g of 2 is going to have to be the same thing as this. So this value, which would be k in that case, would have to be equal to 7. Okay, so that's how we figure out continuity based on this type of piecewise function.